Okay, good. So, so this lab is on the left of the department, high voltage lab, and these are adjacent. So, in this lab, we have several relays, numerical relays, or otherwise you can call digital relays, which are being used in the power systems, both at low voltage level and high voltage level. And in addition to that, we have more modern gadgets we call intelligent electronic devices. These are relays are also intelligent electronic devices, IDs we call. We have phasor management unit, PMUs, which are in conjunction with the GPS-based time synchronized technology. Those are being used. So if someone is interested, we can visit and have a look on these different experimental setups. So what we have done in this lab, that to make it more realistic, we inject real current voltages to the relays as per the requirement from the distribution side, and then we test the relays very close to actual kind of thing. Even in a transformer protection, we'll see later on that we have a transformer and we are protecting it. So yeah, good number now. So we can initiate the process. So first day this is, so I'm coining the word protection. Agree? So to protect the system, which system? Power system. So to mention here, with me, Kuldeep Naik has already joined. So we'll take care of our management part by and large. So the first experiment will go today. But before that, I like to have a background. What is the role of this relays and so? But however, to mention here, we'll have overcurrent relay here. Current is high, then it should operate. So it is verification. So this is a lab experiment. Nothing new to know. I'm saying that we like to innovate here, but existing things are there, and how do they work, and how do you test it? Whether it is functional, its functionality is okay, it is functioning in accordance with the what the manufacturer has provided, so that when you have connected in the grid, in the system, it should function as per is our wish. Because we have fixed it, and we expect that during the required time situation, when the system situation goes through that phases or patches, it should act as per the design, as per the plan thing. So therefore, that is what the requirement of verification of the device relay here. So let me go something background on that. So we say protection. We say protection of power system. Any device, any element in the power system is to be protected from this, for its safeguard, for the secure operation, reliable operation of the system. Like in our house also, all the gadgets, fan, fluorescent tube, trees, air conditioner, all are our elements. So there may be problems at some times, like we call it fault. You all know fault. So this, whenever some short circuit or so, general word, then the corresponding current becomes detrimental, and it may lead to damage of the particular element, and maybe furthermore also. So what happens at that time? So-called short circuit situation. Let us, you can say that this is a source. We can call it a substation or source also. I'm putting S, and then we have some line segments anywhere, and then we have a load. It can be your house premise, it can be substation, line, and so. So this is the load. You can say that is being fed from the source, normal functioning right now, the way it is going on at your end and my end also. But suddenly, due to insulation failure also, at times, not always, very not common. So some fault happens to be there. So when I say fault, it means that typical short circuit also, it can be open circuit also, but in open circuit condition, current will not be detrimental. So during this short circuit, what happens that the phase conductor touches the ground, or the phase conductor touches to the neutral conductor, the insulation failure, and so, or any metallic path, and the metal is already connected to the ground and so. So what will happen? Current will flow through this path, and this voltage becomes substantially low or theoretically zero, then no current will flow to this side. But that does not happen. Sometimes there are reasons you can say that it will not be zero. Some current may flow to the right hand side also. So what happens here in this case, we generally in our terminology call it fault, that when the current flows in an unintended path. Fault is that situation when the current flows in an unintended path. So this current, if we see here, the normal current, whatever the load was carrying out. So in this system, from here to here, the path, the conductor is designed or planned, the system is planned according to the what may be the maximum load in the system. If you put something like very thick wire, then it will be costly, so it is not a proper thing. So whenever a fault happens to be there, see the difference. Now before the fault, that is I call it a pre-fault. So source to load. So for that, if this voltage is, let us say, three-phase load, 400 volt, and then there is impedance of this load and some small impedance of the line. So that is the very total impedance offered by this. So at this point, pre-fault, so V divided by some Z load or plus something, or small amount of delta Z for the line. Okay. So this will be nothing but your corresponding current during load current. Fine. So this is some 10 ampere, 20 ampere, 100 ampere, depending upon the situation and so. Now with fault, if you see the fault situation, so what you see here, that the path now, there is no more load here. This current, nothing but the source impedance, something which we have neglected in this past case, and then the corresponding path, this impedance. Again, this is smaller. It can be fault can be here, and here also, close by also. So that means that the impedance of this fault path impedance equals to much smaller than their load. You agree? Because line impedance is much smaller than your load impedance. Else, efficiency of the system will be poor, regulations will be poor, and so. So that is not a good design or plan things. That is not. It's in any system it is expected. So this Z fault path is very small, so as compared to Z load, and that leads to the corresponding I fault much greater than I load. Agree? So therefore, during this time, the current becomes substantially high. Full load current.
Excuse me, sir.
Current. Yes.
So what does Z fault and I fault represent here?
Z fault and I
I
fault.
fault.
So I fault is nothing but you can say that V, this same V divided by the corresponding and this at this time the corresponding fault path impedance, Z fault. Roughly. Three-phase fault and so we'll talk about more.
So instead of flowing through the load, it flows to the fault, right?
Yes, the path now changes. Okay. Let us say it is a dead short circuit.
Okay, sir.
So then the path is seen. And I told that the Z fault is much smaller than the impedance of the line or the connecting wire is much smaller than the load impedance. Otherwise, it will be an inefficient system. So this fault current will be 10 times, 20 times, many times depending upon this arrangement. That will lead to what? The problem is that it will lead to I square R business now. So I square is the heating part. So any component, any element associated current, this current will flow. If you have a transformer here, through that transformer also this current will flow. And that current, you can say that resistance of the series resistance or that equivalent impedance, if you remember. So that resistance of the conductor of the transformer will also get heated. Any conductor will be heated in terms of its associated resistance. And because this is a square term and the fault current is substantially higher than the normal current, so lateral a lot of heating will be there. But the heat depends upon, when you talk about H, the heat, that equals to I square R into T, time. Agree? So therefore, because of the I square things, the T, with more time, the amount of heat at each element will be also more, and then that may be detrimental to the system. So the fault continues, means the chance of damage of each element is more. Agree? And if you can remove the fault quickly, then there is no chance of damage. So like what you do in our house, we put, you can say, a fuse in series with the supply at the meter end and so, even before the meter also. So whenever this current flows, fault current flows, it melts the fuse and there is a break here, and then the you need to consider replacement of the fuse or restoration of the supply. You know that there is some trouble, you can identify the trouble and make it, isolate that faulted path, faulted section, faulted element, and then you can restore the supply. We have, if now I consider in houses, we have miniature circuit breaker MCB that trips, and again you can switch on the supply. And so if it again trips, you can say that, or the fuse is again blown out, you know that the fault still persists. So the melting of this fuse depends upon the amount of current and the persistence time and so. If it is 5, like you have perhaps done the experiment, the levels of 5 ampere, 10 ampere, 20 ampere fuse. So those fuse is being blown out, you can say, in terms of that. Fine. Now this H equals to I square RT is the governing thing about the damage, fault, and so. If we allow more time, damage will be more and so. Furthermore, it is not only damage, it is the human's life perspective. So safety, you can say, that is another important concern. If the corresponding, like suppose a conductor falls on the ground, then in and around that all portion will be considered. If someone steps there around that place also is detrimental. And you can say that many accidents happens very often in this thing. And particularly it may be detrimental more if a conductor, overhead line conductor falls inside a pond. Cold water will be charged, and anyone taking bath also, you can say that, will be leading to fatality. So these are the challenges. So from safety perspective also, we require that the corresponding faults should be isolated as early as possible. So this is a general background in terms of that. Now we talk about fuse. Fine. But this fuse has a limitation. Fuse has a limitation to address at all points in the system, low voltage, high voltage, and so. In low voltage, also the corresponding current can be several, even kiloamperes also. And in high voltage, both voltage is also high and the current is also high. So if you think about the fuse here, like this, so the fuse, you can say that what happens then, it melts at one point, and finally the melting or breaking, you can say that it can be more and more. The separation between these two ends, two sides, will be more and more. The arcing persists, and then the evaporation of that fuse element becomes more and more till we call restricting voltage, the system voltage, 400 volt, 400 kV or what, this side, that side, by √3 phase voltage in terms of phase to neutral voltage. So therefore, depending upon the voltage, we require, because this side is, let us say, fault means grounded, assume that, and this side you can say that is about your system, the substation side. So this is 400 by √3, let us say our house, each phase. This is now phase A is suppose grounded. So therefore, this is 400 by root 3 volt will be this side and this side will be there. So therefore, a voltage difference between this side will be there. That voltage is responsible for chance of restricting the voltage from left to right of this evaporated portion. So still, till that we can say that happens, that it can sustain that this system voltage, the evaporation continues, arcing continues, and the evaporation continues. So we get that, successfully intervene that one. But see, because of the corresponding inductance of the system and so half Li square and all these things, and with higher and higher voltage, this gap requirement becomes maybe in terms of meter also. Okay, the gap requirement becomes in terms of meter, 400 kV, 765 kV, 800 kV kilovolt, 1000 kilovolt system are in operation today. So therefore, fuse finds a limitation that this is not reliable. Furthermore, in high voltage system, this is voltage, the high voltage, and we have V low voltage. Now the impedance remaining same of the fall point, the corresponding I fall in case of high voltage system becomes much higher than that compared to the low voltage system. But again we square it to find the H, same element. Again it square it, I equals to I square RT. So therefore the I square term will be much higher. So therefore in high voltage system, the time left for us, will be substantially low and small to avoid possible damage. To evade possible damage, the time which will be allowed to a planners or designers is much smaller in case of high voltage system compared to low voltage system, because the possible damage and things may be detrimental at smaller time also. So in a typical time frame, in low voltage system, we talk about in terms of second or fraction of second, and in high voltage system, we talk also in terms of millisecond. The protection requirement, system protection requirement in terms of that. So that is, you can say that about that. So if you find a limitation, then what? So what you require, you can say that we require a switch. We require a switch, which must, you can say that this is switch, which must, you can say that mechanical switch. Physical isolation required to segregate this faulted portion from the rest of the grid. This is grid side from the rest of the grid. If this fault continues, large current will flow through the lines, adjacent buses, lines will be also stressed, and voltage may be down in and around places also. So will not allow this faulted path, faulted things to be there in the. As such, the customers around that feeder will be also affected. But in addition to that, in and around that place also, all will be affected. So it is better to isolate the corresponding faulted path as early as possible. So we require a mechanical switch because fuse find limitation. So this mechanical switch cannot identify, cannot make a judgment. Is it a fault situation? Is it this situation or so? Like fuse of its own way, pin gets melted because of the I square RT heating and so. To this mechanical switch, we need to activate, you need to command, and that command comes from a fault detector. Simply fault detector. And this fault detector detects fault, makes a classification that this is a fault situation, this is a non-fault situation, and accordingly command the relay, command this you can switch to be open. Or it is a sound situation, it will remain in contact. So this is the functionality. So in terms of that, in power system terminology, we call this switch to be circuit breaker, breaks the circuit breaker, and this you can say the detector is nothing but the relay, which senses from current and voltage that the situation is not good, fault situation, and then the commands the circuit breaker to be open. So the circuit breaker of its own way cannot do anything. It has to follow the instruction from the relay. That is the general philosophy. So we essentially require the relay and the circuit breaker in the system. But the relay is fault detector. So earlier you can say that we have electromagnetic relays, then So the evolution of the transistor and all these things, static relays come into picture, and finally we converge to most of the relays available today in our grid are of numerical digital relay and so. Am I audible, Kuldeep?
Yes, sir, you are audible.
Okay, fine. One way traffic. So this
Excuse me,
is
sir.
what the numerical relay came into picture because of enormous
Sir,
benefits.
I think somebody is saying something.
Yeah. Can I
So
hear?
I had one doubt first.
Yeah, tell.
So could you please explain that circuit breaker part again? Like what does it contain?
Yeah. Circuit breaker is a mechanical device. Mechanical device. So there are two plates. Think about simply two plates. They have to be open. Then this physical isolation required so that this the separation should be such that it can sustain the normal system voltage. We call it discharging voltage, nominal voltage, and so. So this separation, mechanical separation of this side plate and this side plate at this point is essential. For that require a switch. It is a mechanical switch. So typically you can see the different types of circuit breakers are there. AR circuit breaker, SF6 is an insulation media. SF6 circuit breaker in high voltage is widely used. Vacuum circuit breaker, vacuum itself is an insulation also. Oil circuit breakers. These are typical circuit breakers you can say that is being used in the power system. So the uh, the the insulating medium, which is there SF6 oil or air or whatever you can say that, is nothing but to make the corresponding arrangement to intervene the system faulted part as quickly as possible. Agree? So it don't require, you can say that I told high voltage system requires millisecond order also. We'll see during our experimentals also how it is being done and so also.
Okay, sir.
So this then what we say that essentially a circuit breaker plus a relay are the essential element you can say that in this business. But the relay being a numerical device, and then the circuit breaker has to be opened through an electromagnetic coil and so required. Agree? It is a very tighten things, and again you have to release and so. So generally you can say that through a coil motorized action and all these things, this being released. So that in that case, we require, you can say that a DC supply for both the business. So battery supply, we call station battery arrangement, is an essential in this part. So these are the three basic elements of a protection system in a high voltage system for many things. This protection is a part of your power system course, but we have, I think the program, the course is started now, so it will be towards the end, or you may not get a chance to also, I don't know. So, but if you see the GATE curriculum also, this is an integral part. So will come across an essential part of the power system also. But because you are still to be acquainted, so I'm giving a background on out of this. And so, what is that relay? We will not discuss here the breaker part. Our discussions, our experimentation here is on the relay part only. Agree? So this relay, you can say that numerical relay, still you will find in the industry in electromagnetic relay and all these things, including static also, because of the cost issue, investment issue, and all these things. But numerical, I can say that it's enormous advantage in terms of that. So just like any digital device, it is a positive points in terms of that self-checking and so and so. One major point you can say that we'll see that you can store the data. You can store the data, and then you can have the postmortem analysis of the postmortem of the system. What happened? Why it happened? Is that the relay function properly, or there is a problem with anything else, or so? We'll see from our how the data are being stored and can say that, and how that is being useful. You can see that in the perspective and so. So that is you can say that one important strength of this one, and there are many more flexibility and all these things in terms of setting changes, characteristic changes, enormous benefits are there. I think we'll go while investigating those things. We'll elaborate more on that. So these numerical relay are being widely used now, and our that focus will be on verification of different numerical in terms of that. But as you notice here, this relay is nothing but a fault detector. So how it will detect a fault. How it will detect a fault? That methodology is different for different relay, and therefore we have different kinds of relays. Like, as you know here, for any fault the current becomes high. For any fault the current becomes high. So we say that overcurrent is a good principle to notice fault. Fine. Overcurrent is a good indicator of a fault situation. So therefore, large current versus small current, that is a very good discriminator to be used in a numerical platform to discriminate fault situation and non-fault situation. For that, what to do? Here we will see also. For that, what to do? No, we have to do that normal situation. What is the corresponding maximum current expected? If you know, and then during the fault, what is the minimum fault current you can say that expected? If these two, there is a separation between these two, 5 amperes versus 10 ampere or 5 ampere versus 20 ampere, then you can make a judgment from this one that no, if it is the corresponding current is larger than this, fault, declare it fault, or if it is smaller than this, keep silent. Okay? So this is what you can say that we talk about simple like current based logic you can put also. Furthermore, simply if you think about that whenever fault current becomes large, the voltage at different buses will be smaller because drops will be happening and all across the system. You can see that at different points close to the fault will be voltages will be down. Another indicator may be that the voltage is down, low voltage. So low voltage situation is also an indicator of that kind of thing. These kind of information features are being used by different relays. And accordingly, you can see that we have different relays in the system. There are for few names I am putting it here. Like we talk about overcurrent, which will start with this. Number 2, you can say that we talk about directional. I'll tell you what is the directional. And number 3, you can say that we have differential. And number 4, you can say that we have distance. Okay. Differential means difference of current. Distance means electrical distance. And direction, we can say that direction of fault. Now, what is the direction of fault? Just to quickly go in. So, suppose you can say that we have a 3-bus systems kind of thing, very interconnected system, not in radial system like in our distribution system. Now, let us you can say that we have a protection arrangement here, load here, and like that. So, this rectangular box I am putting breaker, symbol of breaker. So, breaker here. Now, let us say for this breaker, there will be relay here, R1. Now, there will be a fault here, which is F1 in the forward side, and there is fault can be here at F2 also. So, this breaker I am hatching it, this breaker should operate only for F1, not for F2. Only for F1, not for F2. Why? You see here, if this you can say that breaker will open for F2 also, for F2 fault also, then this load cannot get energy or power from right hand side at that time. So better for F2 fault, this breaker should be operated. So the relay at R1 should have a discrimination capability. Current can be for both sides, you can say F1 and F2 currents can be substantially high. So overcurrent will not able to discriminate that. So require discriminations whether the fault is in the right side or left side to operate the proper circuit breaker, this breaker or this breaker. In that case, let us think about the relay R1 has to make a discrimination, has to be able to discriminate whether the fault is in this side or in this side. If it is in this side, it will operate the breaker, this breaker, or it remains silent. For this breaker, there will be another relay. Thing like that. So therefore, we require a directional information, and directional information means information of the direction of the fault with respect to the relay or the measurement point. And that is what we talk about directional information or directional relay. So differential, current differential, and just in one quick nutshell, you can say that I can elaborate with you. So this is a current differential I can put for a line or transformer. So I'm putting like this. So what you do here, this is current I1 and this is current I2. So whenever then internal fault, just have a thing like that. Just whenever an internal fault, normal situation I1 and I2 magnitude will be same. Normal current flowing, I1 and I2 magnitude will be same. So I1 minus I2 or I1 plus I2, the difference current, depending upon the direction, CT connection, polarity connection, and so. So normally we say consider that, let us say thing like that. Difference means I1 minus I2 will be 0. But whenever internal fault happens to be there, these I1 and I2, the I2 current now reverses. Earlier current was flowing from left to right. The I2 current from, you can say, sources will be there, I1 and I2 will be there. Or if it is radial systems, I1 and I2 will be no more same, because the fault current will be substantially high and this side current will be much lower. So there we consider a difference I1 and I2 will no more 0 during internal fault situation. So for this line or this element, whatever it may be there in between, that can be clearly, we can make a judgment of internal fault or external fault situation or no fault situation in the system from this I1 minus I2 or a differential current we call. So those are the things. And then to a background of distance, we'll come to later on more also. Distance, that think about this. Suppose this is a transmission system, this is a transmission line or line, whatever you say that. And now you can say that, think about general idea that we like to have the impedance. Now what is this impedance? Simple, at this moment you take about V divided by, it's simple, V divided by. So whatever voltage, whatever current is going will depend upon this impedance plus the load impedance. So normally, if you have a voltage and current signal and the numerically is able to calculate this voltage and current and find this impedance, so this impedance is nothing but the line impedance plus this Z load impedance. Much higher. The impedance will be much higher normally. But when a fault happens to be there, so the impedance path will nothing but this path. So Z fault will be V divided by, consider I fault. And that will be much more smaller than this current, this impedance. So what you notice here, that during fault season, the impedance seen by the relay, called impedance seen by the relay or calculated by the relay, will be much smaller than the normal situation impedance. So this is also indicative of fault season in terms of that. So the point here is that why there are different relays, from this you can make a judgment that to perform better way, to discriminate the faulted path versus the non-fault path, sound part of the system. So that
Sir,
discrimination, yes.
so how can we avoid the fault paths, like in the internal faults?
How can you avoid?
How can we avoid the fault paths?
Avoid means, are you talking about avoiding fault?
Yes, sir. Yes, sir.
Okay.
In the
So
situation of
how?
I1 equal to I2.
Oh, I1 equals to I2 in the differential. Here you are talking about.
Yes, sir. Yes, sir.
So what do you like to say? Tell.
So if the fault doesn't arise, then I1 equal to I2, right?
Fine. Yes. Yes.
So how can we come to that situation?
Which situation?
Like, is there some practical ways to avoid the faults?
Okay, that is what. Yeah, I got your point. So what do you say that can fault not occur in the systems, like in overhead ground, overhead line. So sometimes a storm
Yes,
comes
sir.
into the line, conductor will fall on the ground. The insulators we know, string of insulators, porcelain insulators are there, 10, 20 are there depending upon the high voltage system. So there will be some lightning strikes, they get damaged. So that will be a short circuit path. This happens very rare, but it will happen. Even a cable also gets punctured because of the lightning and so. And then there is aging effect also. Transport due to aging effect also, there can be a fault also, rarely. So what we like to say that if you have preventive maintenance good and know, you can say that know the corresponding weak points and so, then you can avoid against that faults as many as possible. But complete avoidance as of now is not that easy. Agree? So because we like to have um, different issues like natural calamities and so also.
Okay, sir.
Got the point, no? So complete, what you say, like in our system, in IIT Kharagpur, we have supply from 33 kV system, and then we have step down to different transformer, around 15 transformers. We have 11 kV network, ring network kind of thing. And from the 11 kV voltage, you can see that transformers we have, our electrical department has 3-4 transformers around that place, and then we are feeding to the different loads. So because our whole 100% system is underground with underground cable facility, so hardly any lightning issue, and so we don't, the failure chance is very rare. Agree? We get the very reliable supply, and so true, because chance of fault is rare. Earlier we had overhead line, so many times if something and something have it, I answer that the tree touching, you understand, you can say that tree touching, even you can say that bats, monkeys, anything can interfere, you can say that, and lead to fault also. So those, you can say that chances are rare in this kind of thing. So what you like to say that to reduce the number of fault, today you can say that even I think you know, I'm saying that at Nest central level also there is a big initiative that all cities should be having underground cable, and so like Varanasi and so doing, and also in West Bengal also there are many, you can say that township areas are being taken care for underground cables, and so because of the reliability perspective. And as I said, fault versus reliability, more faults, less reliable, less fault, more reliable. Okay, is it okay? We'll proceed.
Yes, sir.
Okay, so this is something on general idea about what is fault, why it is detrimental, and then what are the different types of relays, circuit breakers, scope, and so. So I think that idea will go to our today's business on overcurrent relay characteristics. So the very fundamental things about that is that our focus today is on overcurrent relay. Really? Overcurrent relay. So what is this overcurrent relay? As you say this, when I is high, then it should command the breaker, we call trip. It should issue a trip command to the breaker to be open. That's all. But this judgment should be pretty good. One point I'll add here, that let us say we have a system like this. From the substation, there, this is substation. I'm putting it a symbol of synchronous generator. There is a substation there, and we have different lines coming out of that to the transformer 1, transformer 2, load area 1, load area 2, and so. Suppose a fault happens to be here in this branch. Is it that this branch should be affected? No. So it means that our relay, breaker here also, our relay and breaker arrangement, the protection arrangement should be such that whichever is the faulted, means that part, faulted segment, faulted line, that should be only isolated so that other customers should not be affected. Is it okay? So this is called selectivity. This is called selectivity. If you put, you can say that breaker here only, and then you put a relay, then all you can say that you like to break, you can say that the whole system will be in problem without supply. So that's the earlier directionally also example I put you, that this side or that side. You can I can go back to that side portion also. So yeah, here in this case, if any fault happens to be there in this whole area, whole region, then I can put a breaker here and trip hold this. Then all loads will be affected. So that is not desirable. So therefore, in selectivity sense, we like to isolate the faulted section only, not to the rest, so that maximum you can say that customers can be still retained in the system, and so. So the overcurrent, you can say that, should also look into that also. Really, all relay and all these things should be look into that. Okay. So before starting, we have a setup. Here, this is the relay. This is the relay. Agree? Alstom make. We'll come to that. And numerical relay. So this device is connected to the PC. This device is connected to the PC. So we can connect to PC, control, command, setting changes, data recovery, all things we can do through the PC. And then we have, you can say that, a setup arrangement to inject current to this device, because this is a over current, so its input will be only current. Its input will be only current. If it is an impedance relay, we require voltage information also. This is a three-phase relay, so require IA, IB, IC, three considered currents to be input as input to this particular relay and so. And these are about measurement systems and so. So this is about current transformer also. Current transformer we require, you can say that. See, in a system, the level of currents can be thousands ampere and so also, particularly during fault. Even during normal situation also, it can be 100, thousands ampere, depending on the capacity of the particular feeder line or device. So therefore, because this device is a numerical device, 5 volt, 10 volt input device, so we cannot have thousands ampere input to this such device. It cannot manage that. If we do that, then the corresponding size of the device and cost of the device will be too high. And this part is nothing but, you consider, a detector part. This part is nothing but a detector part. So why should we consider that have a detector which will be similar size of a transformer or any device? Agree? So that is not investment wise also not welcome in terms of that. So therefore, what is being done, that to downscale the current, we put current transformer, you know. So therefore, this current transformer typically a single turn in terms of that, and multiple turns to the your secondary side, so that the current becomes substantially low, and that low current, you can say, that becomes an input to the relay. But all these, you can say, the relays, microprocessor, microcontroller, they contain. So the input to them is only voltage. Input to them can be only voltage. So the corresponding current has to be converted to voltage. But that is internal to the relay. The relay does that. Agree? The relay does that. And once we have this corresponding current proportional to the voltage, and this voltage is being now sampled, processed, digitized, and so and so. Okay? That is what the process happens to there. So here in this arrangement, we have current injections to the particular relay and see that whether it's functioning properly or not. What is properly or not, that we also try to see. So purpose is verification of overcurrent relay characteristics. Now, what is relay characteristics? We'll see that. Why do you require characteristics? This is required from selectivity point of view. There is another term will come also in terms of coordination perspective, and so we'll see what are the different ask or requirement from a system protection perspective, so that the relay does accordingly. And I told you that it is not that anywhere it finds the corresponding current to be high, the relay should trip or no. It has to be a way, in a selective way. It should isolate. If really it identifies that the corresponding fault is within its jurisdiction, within assigned section, we call it zone. Agree? Each relay is assigned with a zone or area, so it should look after that. If the fault happens to be beyond that zone or assigned area or line or segment, it should remain silent. That is what selectivity says to us. So what you will see here, some theory behind that. And then we have a certain objective to verify this. We'll see the circuit diagram. Settings, how will change, and what are the settings, how to be done. And then the observations and how to verify this one. So at the end of this discussions, we'll have few sets of readings, so that observations, just like what students come and do in the lab also, they collect data in the after the these kind of the all the connections making here, and then they inject the corresponding current to the device. There are specific way you consider how to do that, and then you consider that they collect the data, and then these data are being analyzed, plotted, and verify, and so and so. We'll see that. But what I say that what we are discussing are, this is also available how to connect and what are the elements and all these things in the lab, in our own lab here, about the YouTube also channel. The link is also available. You can see afterwards also. So the way I talking about the numerical or digital relay. So we have a V, current, voltage, and so in this case current input. Also, you can have a discrete input also, like a command from other relay, adjacent relay, that no, remain silent, don't trip. This is my job, not your. Like that kind of thing. Agree? Or from the remote relays also that no, the corresponding current information and so can also be there into the system also. So this can take just like any, you can say that digital device and so. It converts the analog to digital conversions, and then we have the processor like my laptop and so. This processor will now takes the corresponding sample and does use these corresponding samples to find the required things, and then find, you can say that a trip command and so, trip or no trip to remain silent and so. So this is what you can say that it can communicate to others, it can operate the corresponding circuit breaker and so. So this is as simple as that. Input analog signal converted to A to D digital signal, process it like the algorithm part, the brain part of the important part of the relay. Otherwise, the called the protection brain of the protection. You can say that system is nothing but the relay, and then it derives the corresponding trip or no trip to make the things to be there. It is as simple as that. So if you see the, you can say that signal flow path, then current or the voltage signal, they are being scaled down. Current is being scaled down by the current transformer. 100:5, 1000:5, 800:5, that kind of transformation. And voltage also like 100 kV system, 1000 kV system, 132 kV system, 400 kV system. The corresponding voltage has to also downscale to 10 volt, 5 volt, and so. So this you can say that about the potential transformer, or the current is having current transformer. So this transformation or scaling down happens to be there, and then we have a analog to low pass filter like spikes, etc. can be avoided, we can say, in terms of that, so that for the security of the particular device, electronic device, and so. Then you have this analog to digital conversion, and then your digital filter here means the algorithm part. Agree? The algorithm part. Which algorithm? The relay algorithm. What is that? The decision making process. Its current is high, its voltage is low, and the differential current is substantial. This and that. Very simple way that I am talking about. But now you'll see, you can say that no, it is not that one. It requires certain characteristics, curve, and so on to verify and so. And then you can say that you can call it compute the impedance also and so. And from there you derive, you can say that the tree decision. Now after deriving tree decision, what you'll do? It will communicate to the trip coil. We call it trip coil of what? For the circuit breaker opening. For the circuit breaker opening. This is what the need, you can say that, is from a particular relay. You can say that is being required. Fine. So when you focus about relay algorithm, input, current voltage or whatever required, filtering part, then we'll see some computation part. We call phasor estimation, harmonic calculation, and so. The term phasor is coming here. I like to say here. Am I audible, Kuldeep?
Yes, sir. Yes, sir. You are audible.
Okay. So phasor is called. We know all phasors. You can say that in electrical technology, we started with that also. So this phasor, voltage and current phasor, and then we relate to the impedance. So whenever you talk about impedance, it is nothing but R plus j omega L. This omega corresponds to your 50 hertz or so in our case. So when you talk about impedance and you relate to the voltage and I, these voltage and currents are nothing but not the RMS voltage and currents, because not the RMS voltage or currents, rather they are fundamental component of voltage and current. Why we are talking about fundamental here now? See, whenever a fault happens to be there in the system, let us say this is source, the corresponding current and the voltage goes to the transient process. Agree? It goes to the from the normal situation of R and L, now it goes to another R and L. So this current, you can say that, let us say normal current flowing is like this, and then this suddenly the current becomes like this. At that time, voltage will be low, and that will be also distorted. So therefore, from the distorted currents and voltage, we have to extract the fundamental component, because unless you use the fundamental component, your analysis, because you analyze the system in terms of impedance is essential, R, omega, L, and so in general. And therefore, you can say that we call the fault analysis when you study in your this power system paper also. There are sequence component analysis and so. So when you are using the current concept of impedance and that to particular frequency like 50 Hz in your case, we essentially require the voltage and current also 50 Hz. But during normal situation, we generally say that the voltage and currents are fundamental component. But during fault situation, that is not correct. So therefore, you have to extend the corresponding fundamental component out of this. And that's why we are talking about the phasors also. Sometimes the harmonic components are also required, particularly in transformer protection, inrush situation. So whenever we switch on the transformer, the inrush current flows 5 times, 10 times the normal current, without loading also in the secondary side. So that current becomes is not detrimental, but that is not a fault situation. So even the current is high, the relay should not trip. To distinguish that this is inrush or not, harmonics is being estimated. Like the corresponding current patterns become like this, not symmetrical along x-axis, time axis. So this contains a lot of, you can say that, second harmonic component. So if you estimate the second harmonic component and with respect to the fundamental, then you can make a judgment that yes, this is inrush situation or not a fault situation. So that's the point. You can say that the relay does that. So that's my point. You can say that we require here essentially phasor estimation perspective, and then the protection logics, and so we put, you can say that, or relay logics in terms of that, and then make a trip or no trip, no signal, and so in terms of that. So this is about the background of how the corresponding numerical relay acts, you can say that, using this one. To have a basic idea how the phasor is being computed, and I told you that don't go for a simple RMS. RMS is inclusive of all whole signal component. We talk about rather you can say that you extract the corresponding 50 Hz component or the fundamental, and then you can say that peak by root 2 gives you the RMS of that, only one signal. Then we talk about in terms of that also. So here purpose is that how to get the phasor. So it is a digital filter, Fourier filter in general being used by this one. There are other options also. Yes.
Can you once again repeat why the fundamental is needed? I understood the harmonics.
Yeah. So you see is that we use the network analysis by impedance. Yes. Tell me, yes or no?
Yes. So we will calculate that only for fundamental.
No. We analyze the system, network, this and that, through which we design the, you can say that, the corresponding relay, how much current we will see, what is the voltage, and so and so. So our network analysis, you can say that, is being through Z, which we use to design the system, including protection system also during fault. Agree? We'll see in your teaching also. Now, if you are using this Z is nothing but R plus J omega L. Yes or no? This omega is nothing but your 50 Hz. But there are relays and all these things which you can develop also without using that also. Fantastic. Now today it is there. I'm not going to that. Only is working on traveling wave also. Very. So, but this is what the common philosophy you can say that with you. Now the relay you can say protection system is designed based on this impedance. Now for this impedance, how will find this? Using voltage and current. Which voltage and current? No. This is fundamental, means the corresponding voltage and current also should be fundamental. Because during this fault, it goes through transition. So there is this transient voltage and current, and they distorted, they are not perfectly sinusoidal like normal situation. So you have to extract their corresponding fundamental from that distorted signal. Agree?
Yeah.
Fine. So to have that, you can say that typical algorithm, I can say that Fourier based algorithm, we call discrete Fourier transform algorithm. Rather, I can say that one cycle DFT. So one cycle in 50 Hz system, one cycle is nothing but 1 by 50. It corresponds to 20 millisecond. So we take a window of 20 millisecond and we get the corresponding samples here and use this, okay, to extract the fundamental component, which will be used, you can say, for different calculations and all this thing, including in the overcurrent relay, including this overcurrent OC. I'm writing overcurrent relay OCR short form. So in overcurrent relay, you can say that we bother about I. Someone will think that cannot not you consider take the RMS value, any RMS value and do. Yes, that was being used consider in case of electromagnetic relay and earlier form of relays and all these things. But see, what we are deviating, our analysis, our design of the protection system is based on the impedance-based perspective, means it is fundamental, 50 Hertz. But when you take a distorted wave and take the RMS value, then that is not correct. Decaying DC will be there and so also. So therefore, if you can get the corresponding 50 Hertz component, then it will be in accordance with your design philosophy. That's the consider the decision process will be more accurate in terms of that. So that's the reason you consider that even for the overkernel also, the today's numerical relay does this fundamental extension and this. So let us say this is about the signal samples. Yes.
So like here, if you only consider the fundamental part, the other harmonics it will also dissipate power, and it will also it can also cause harm to the component. So like if you don't consider the other harmonics, if you only the control logic is based only on the fundamental, won't there be a problem?
Yeah, not a problem. See what I told that suppose as you are saying he's correct. Consider that you can from the high frequency component also you can make a judgment. What Kuldeep is doing, tell me I am good. Kuldeep you consider is working also. Let us consider that whenever a fault happens to be there, we'll have a traveling wave. There will be sudden change in voltage and current. So that will you consider propagate waves you consider will propagate from this side to that side. So that can be also used here. But mind it that the purpose of here the relay is to identify whether there is an internal fault or not. So you can use harmonics, you can use traveling wave, you can use you consider fundamental also. My point is that if your design philosophy is based on the Z and that is on the 50 Hertz component impedance omega L, then you can say that you have to go with the 50 Hertz. If your design philosophy is based on the like in transformer case I told that your design philosophy in harmonics component, then you have to think of harmonics perspective also. So you can use this and that. But what you say is correct that yes, the harmonics and all components will be responsible for possible damage. Yes, our purpose here is that to identify whether that the fault is internal or external or there is no fault. To have that discrimination function, we are using certain features. You can use fundamental 50 Hertz, you can use harmonics, and you can use many. And enormous varieties of things are there, which are you are using in this case is your fundamental focus. Is it okay?
Okay.
Yes. So now we can say that we talk about what is that phasor estimation process and one cycle DFT and so. So let us say this is the signal. This signal will be considered as I say samples like this. One after the considered samples will be coming. So this is 8 samples per cycle. In 20 milliseconds, we are acquiring 8 samples. Then you can get the corresponding sample value like this. So typically, you consider relay use less than 3 kilohertz or so sampling rate kind of thing. 1 kilohertz and around that is there. That depends upon you consider the corresponding things also. Someone will say that no, I can sample it higher frequency rate also, higher sampling rate also. Yes, true. That will reveal more details of the signal, but the cost of consider will be more and more. There are two costs associated we can think about in terms of that. Suppose we have a signal like this. This is delta t. This is delta t, intersampling interval. If the sampling rate is high, delta t will be small. But unlike that, what happens here, this is fault progressing. Let us say something, fault is progressing. So will not wait one cycle, will not take 2 cycles, 3 cycles to make a decision. Our window also goes on shifting. Every samples the window has to shift because it is protection decision. The faster, the quicker you can make the decision and treat the circuit breaker, safest it will be. Agree? Otherwise, that again same H equals to I square RT will go on the thing. You allow more time, it will damage. So therefore, unlike any mechanical system also, you wait for a long period and make a judgment, will not allow that. To have that, you can say that fast or quick operation of these things, this window, one cycle window called moving window, is shifted every samples the relay acquires a fresh sample. So therefore, within that intersampling interval of delta t, the relay has to acquire the sample and also compute, is it a fault situation? That questions always it asks. It means that it has to rerun its own algorithm, main algorithm, always. That is the main difference in case of numerical relay. So therefore, if we make the corresponding systems to be more sampling rate to be higher, intersampling interval becomes small, and your processor capacity strength has to be high. And that's the reason cost will be also high. Agree? Kuldeep is now facing problem that he requires 1 megahertz sampling. So people, the cost associated is very, very high in terms of that as compared to 1 kilohertz or 3 kilohertz sampling rate in terms of that. So now the point here is that the voltage phasors, we have a Fourier coefficient E upon minus j 2 pi small n capital N. Capital N is the number of samples in one cycle, and small n you consider every sample 1, 2, 3, 4, some 7, 8, whatever samples will be there in that window of one cycle. So this is what the Vn is, the nothing but the corresponding this Vn, the sample 0, 1, 2, 3, up to 7. In case of n is 8 means it will be 7 samples, 0 to 7, 8 samples will be there. So each sample will be multiplied with a particular Fourier coefficient like this. And then you can segregate also real part, imaginary part out of that. And then you can compute the corresponding phasor here, V real minus j omega with the V theta or so. Okay. And then the V imaginary in terms of that. And we can find the magnitude also, you can say that in terms of the real square, something like that. Okay. So we once you get the corresponding complex number, real part, the magnitude part and the phase part, the angle part, you can obtain. That is the phase information of, yes.
Sir, in the Fourier computation, why there is the extra coefficient root 2 by n in front of the summation part?
Yeah, this is to get the corresponding RMS value. We require essentially the RMS value to get that one. That's the only reason. Agree? Finally, you should get one. You get the peak value, so that's the corresponding things has to be considered multiplied. This root 2 by n factor is only to get the corresponding RMS value. We'll see consider in the calculation process and all these things. As an example, agree? So, but this is a theoretical background I have to put. This is not experimental part. This is what the relay does inside that I'm trying to say. So let us say this is a signal. We have simulated signal. We have taken something like 109 or something like 100 pi t 22.2. So this is the signal generated. So I was telling you this is the window 1, this is the window 2. Each you can say that sampling interval. When it goes to next samples, the window shifts. So we call moving window with a new cycles. So this is what you can say that the number, the samples which will be given, the blue one will be window 1, will be from this to till this. When in window happens to be there, it starts here and ends here. So it discards the older sample and acquires a fresh sample. Agree? So this is in a steady state. There is no fault here for your information. And if I apply the corresponding things, this is the time information, and this is the samples you can say that which we saw from this diagram. And these are the Fourier coefficient cos and sine. And then you multiply them, you can say that in terms of this to find the corresponding real and imaginary component. See, you add them summation of this for the 8 samples here, and then you got this to be 165, this is 405. And when you use this, you can say that for my phasor computation, I get the corresponding phasor to be 77.45 with an angle of minus 67.75 degree. This is what the calculation process. This is for window 1. Now when we go to the window 2, now the sample is shifted. Now the samples are not changed. Older sample is discarded, new sample is being acquired. So this is the new samples required. Same for your coefficient. Same 8, you can say that weights are there. 8 here and 8 here are there. And you multiply to these samples like that, then I get the corresponding summation of this real part and the imaginary part to be like this. And when I apply this in window 2, I got this corresponding 77.45 with minus 22.75. Only that change if you see here, this is 67 and this is 22 here. A shift of plus 45 degree happens to be there. Ready? Magnitude remains same. Why it remains same? If you see this signal is nothing but a steady state signal. No fault, nothing. So what will happen here? Same window, same RMS value will be there. Fundamental component. Peak divided by root 2. That's why you are getting 77.5. This 109.53 divided by root 2. RMS value. Agree? And then the other point you can say we are getting that this window 2 has shifted by a forward of 45 degree. Why 45 degree? 8 samples per piece. So 20 samples gives you 360 degree. sorry, 20 millisecond, 360 degree. Now we have 8 samples. So 360 degree, 8 samples. Every sample interval divided by 8, so we are getting 45 degree. So that 45 degree of advancement, you can say from minus 67.75 to minus 22.75 we are getting. That means that the phasor which is indicative of obtained from this one is indicative of angle also correctly. So when we compare two voltage, one current or two voltages, same window environment. This is one signal, this is another signal. So we have taken the same window. So I can know that the corresponding V1 and V2, what is the angle between these two? Correct? One will having certain angle, V1 with an angle of something, and V2 will have angle something. So you can know that what is the angle between V1 and V2. So this clearly shows that by computing such phasor, we can know the voltages between two phasors, current, voltage, whatever it may be. So now we say that by computing the corresponding phasors from the signals, voltage or current, in our case over current it is current signals, the relay can find the corresponding RMS current of the 50 Hz component, RMS current of the 50 Hz component faithfully, numerical platform. Now come to the working principle of overcurrent relay. How does it operate and what is that overcurrent principle? What is that characteristic?
Sir?
Yes.
So like are there always two windows, like, or we can increase the number of windows for calculation of the phasors?
Once again, can you tell me, are they?
So like do we always use two windows for calculation of the phasors, or like we can increase the number of windows for the like calculation?
No. A very good question. Consider that. What we say here is that the fall progresses. The fall progresses, and the corresponding relay has to make a decision. If the relay has not decided till now, then the relay goes on acquiring data till what? Till the corresponding decision is being taken. So it is not one window or two window. It is a continuous window, you can say a moving window, till the relay takes a decision. Furthermore, I'm telling you that relay takes a decision and commands the circuit breaker till open, but the window still goes on till what? The current becomes zero. And why do we require that? We don't know whether the circuit breaker will open or not. Even the circuit breaker will it open, you can say that correctly or not? How much time it will take? All are uncertain. And because the relay has the capability to store the data, the window will go on moving forward till this one. So for the decision, however, as we are saying, that the relay, you can say that will go on continuously. You can say that for this corresponding fault signal also, you can say that the window will go on moving and moving forward. You can say that till the current becomes zero in that path, and so. Agree? It's not one window or two window. It continues till the decision process. Also, furthermore, you can say that to record the event properly in terms of that. So we know an overcurrent by this background. An overcurrent device operates when the major current exceeds a predetermined threshold. We call it as pickup current. Pickup current means that is the minimum current above which you can say that the relay should operate. So pickup current is a setting current. Pickup current is a setting current, is selection current. When the fall current is greater than this pickup current, the relay should operate. Maybe. So that is what the principle first step we are talking about. Now there are two situations. If the current is high, then this one setting, then should it trip instantaneously or it will delay the process? Now there is a question here. In a distribution system, this delay or instantaneous is governed by that same H equals to I square RT. Can you delay it or can you not? Now, delaying has exactly advantages as of now? No. I've understood that this sooner it should trip better. But very peculiar in the power system. Most of the faults in a power system, 70% faults in a power system are self-healing. They come and they vanish. They come and they vanish. So we call it intermittent in nature. So therefore, can I wait, watch? If it vanishes of its own way, then I need not interrupt. If I interrupt, then the reliability of the system becomes poor. Unnecessary tripping means our customers will be in problem. They will not get the supply. Power supply will be not there at that time. So therefore, it is better you can say to wait and watch if it is allowed. Who will allow? This will allow. So in a distribution system, because we have current magnitude is small, fault current as compared to the high voltage system, so I can allow some time, agree, which will not lead to damage or any stress to the system. That is what I'm telling. So you can allow some time. So that's why can I use a delay, little bit delay, or it is instantaneous? That is the question. Okay. Furthermore, this time frame is also a discriminating factor. We'll see later on in terms of that. So purpose is to discriminate fault and load and isolate the faulted section selectively. That's what I talk about. Agree? The reason you can say that in this portion or that portion, is it a permanent fault or not a fault? Permanent fault, you understand. In terms of most of the faults are not permanent. 30% faults are permanent.
Sir, how do faults vanish?
Yeah, again, can you put your question?
Do faults vanish?
How?
Like how do they disappear?
Not audible. Repeat.
Am I audible now?
Yes.
You said 70% of the faults are like self-recoverable or something. So like how do they
Yes.
recover?
Yeah. So like let us say one day I was visiting at the Kanpur campus some region, and then I saw in the morning walk, you can say that a bat on the morning time, bat on the live conductor overhead line. That time campus was having overhead conductor. So what would have happened? That I died. So you can say that two creatures or two bars. Bat is not a bar. So or bat touching two phases means it will be getting a 400 volt supply, and then it is or two bats also. So then when we topology, you can say that it will die. But that is a very small event for the power system, so strong power system for the distribution system. So at that time, what will happen? Whenever there is short circuit, temporarily the current will flow. But that doesn't mean that the system should interrupt there. Even a monkey and so on. So So it is a momentary, and then it vanishes of its own way also. Many times what happens also, a tree touching and again going back. Okay? That kind of thing. So it is that's why it's happening. But as you say, pointed out rightly, cable. In cable it does not happen so. Cable faults are permanent. But in cable rarely will it happen. After aging or some happens when permanent fault happens when mostly can say human intervention. Like in many roads in Kolkata metro, if you go there, if the water can say that supply people will extravagate, so that go for pipelining and so unnoticed, you can say that they call the cables and so what the question was about that intermittent things, how that happens is that even it is a sub-circuit, if that remains for smaller period, it may not be a matter of fact. But if you think about the high voltage systems, even that period may be also detrimental, not from we can say that system damage perspective, from stability perspective also. I think during your course theory you'll see that how that may lead to instability in the system also. If the fault persists for a period of time, that may be very called critical clearing time and so comes into picture in terms of that. And there we require the speed of operation in this. What is being done for your information that now this we can put more intelligence to this relay. We call reclosing phenomena. Any fault happens to be there. transient, transitory, permanent, whatever, trip it. And again switching off after a, something. And many times you must have seen in your that system that again the system is restored after some time. Agree? And that is what nothing but called auto reclosing. We call it that auto reclosing. Trip, auto reclose after some time because most of the faults will vanish by that time. Okay? So auto reclosing in a transmission system and so is being very common in that perspective. So to avoid that, and this permanent fall versus the transitory fall is more common in a high voltage system. But in low voltage system, if you have cable, you can say that most these are permanent falls. And so, is it okay? Fine. So we'll proceed. Now, the algorithm for the overcurrent relay includes a threshold pickup, which is a discriminating point for fault versus load discrimination, overcurrent, load versus fault. I can put, you can say that this is load level, maximum load level, and this is the minimum fault current level, minimum fault current level. So in between something I pick up, so that the current when it crosses the load and crosses the pickup, then we adjust the fault. Sometimes momentarily, not here. Sometimes momentarily overload will happen. Suppose you are switching on a motor or so. Sometimes momentarily it will go for this. It should not trip. Okay? Otherwise, it is unnecessary tripping. Momentary load growth happens to be there. Switching on some growth means current is being quantified in terms of that large current may flow for some time. But that is not true. Like you talk about whenever you switch on it motor, then starting current will be high. But should the protection trip? Is it a fault? No. It's a normal operation. Like inrush current also I told you. So a transformer in the downstream switching on, inrush current will flow. In the upstream, you can say that the relays will see that the currents are high. They should not trip. They should wait and watch. One point. So that's the point. So fine. Accordingly, the pickup setting and so are being then, and then the time should be there. Compute the RMS value of the fundamental component. Oh, the relay confirms a fault if the measured current is above the threshold. Command or trip considered vacant because of the with a delay or without a delay. When you talk about it with a delay, to have that flexibility in the system, selective way and so, then we are talking about introducing a time into the decision process. We are introducing a time into the decision process. How much time? You can put a question, how much time? Again, same H equals to I square RT I can put. So what you can see here, I can allow the time to be longer if the fault current level is smaller. If the fault current level is higher, decision time should be smaller. Trip command time should be smaller. That is the simple logic. So, but however, because square term of current is there, so it should be non-linear. And that's the point comes inverse definite minimum time characteristics. We'll come to that. In numerical relay, in analog form of relay, there is no brain calculation and so. So whatever CT secondary, you understand CT secondary? So this is the CT secondary side. CT secondary current gives that current actuates the relay. So relay sees only that current. But in case of numerical relay, you know the CT ratio. So once you have the data input that is required in the CT, in the numerical relay, the relay can calculate the what will be the corresponding primary current. Primary means system side current. So that primary current, system side current can be directly used by the relay to make a decision. What is happening in the system? It can know better way. And that you can say that is being used, you can say that by the numerical relay perspective. So we have to enter the corresponding CT ratio for that perspective. Types of overcurrent relay. Work now categorizing them, means that two relays, phase and ground. Phase relay and ground relay. Okay? I am giving you two situations. Let us say we have three phases, A, B, C, capital A, B, C, or small a, B, C, whatever. Now here, suppose it is grounded. So current from this substation side, current will flow from this to this path and this is the fault current. IAF, that one. So it is a ground. It is grounded, agree? Because system is neutral, is grounded. You know, typically you consider this is the star ground. You consider to the low voltage side, delta to the high voltage side. In a 11 kV is to 415 volt supply system and so. Therefore, this is considered a grounded system. So in this path, you consider we see here in this phase, phase A is having large current, not the other two phases. Now think about another situation. This is A, this is B, this is C. Suppose there is a short circuit between these two. Someone puts a chain, like during maintenance time, people put a chain across all three, so that even someone at the substation and switches on, then if you put the all three considered, to the right hand side voltage will be 0. So it's better you can say if you are working in this area, so put a chain like this. Agree? So even someone at the substation side or switches on, then it will not be detrimental to this side. But many times what happens, the maintenance people forget to remove this, and whenever the switches on, so it becomes a dead three-phase short circuit. Like that situation I'm telling you about. That suppose you can say that two phases are there, phase A to phase B. So currently from what? Here to here, IA and IB both will be similar magnitude, same magnitude. The current will be high between this. There is no ground current here. There is no ground current here. But ground currents are more common. 70-80% faults are involved with ground. Agree? So therefore, you can say that, and we'll see. You can say that the ground, you can say relay. You can say that how to have this ground current and how to have these phase relays using the phase current. That we'll see. In phase relays, we say that the fault is not involved with ground, but in ground relays, we say that the fault is involved with the ground. And we'll see. You can say that the ground relays are more sensitive also. You understand? Sensitive. Agree? I am more sensitive to something. So that sensitivity is having high in case of ground relay. So it can identify the fault better way if the fault is involved with ground. We'll see that. So the connection for these IA, IB, IC after the CT connection to the relays are like this. And I'll put, you can say that different numbers are there, 50, 51 and so. So these are, you can say that relay numerical relay terminology we call IEEE, you know, and the ANSI, American National Standards Institute. There are relay numbers. The power system engineers, they know what is 50, what is 51, what is 51 and 51, and you can say that is about that ground relay and for neutral. And 50 versus 51. 50 is for instantaneous, and 51 is with time. We call inverse definite minimum time analysis. They are put time information, but 50 is instantaneous.
So are those coils current transformers?
Yeah, hello.
Are those coils current transformers?
Yeah. We put a symbol like this. This is our CT. And in case of PT, you consider if it is a boss, then you put consider something like that. Okay, this is about the PT. Scale down the corresponding voltage and current to low level for the relay connection perspective and so. So here what happens that, hello, tell.
Sir, these are internal connections or like these are external connections here?
No, these are external things. This is in the system side. You put the CT at the particular location where you like to measure the current. And these, you can say, wirings are being taken from that system, from the transformers or wherever you're measuring, or the bus, to the, you can say that this is, you can say, the control room. This is the control room. And the control room, you can say, will find several relays and so. Okay. Hundreds of relays may be there also in a big substation, thousands maybe also, to take care of different protection perspective and so. And these are nothing but numerical relays. So they can, these numerical relay, another thing I'll point to, they can have 50, they can have 51 function, they can have under voltage, high voltage, they can have over voltage, they can have impedance, differential, all. In our lab, if you come, you can see, same you can say that relay, REL 651 or 671, or you can say that relay and so, they are called multifunctional relay. we call it as multifunctional relay. They can do multitasking. Overcurrent they can do also, they can do, because current voltage signals mean they can compute and process anything in terms of that. Okay, let us go to our business. So in this numerical relays, you see, you can say that one thing, what is that ground current we are talking about? Residual current, ground current, and so. So what we say here, you'll study, can say that later on the phasor analysis, fault analysis, and so. This IA, IB, IC. So if you add all these things, normally this current is 0. IA plus IB plus IC is 0. That you know. But whenever there is a ground fault involved, let us say phase A current. So phase A current becomes substantially high, and B and C are like that. So if you add that time, you can say that this becomes not there. Or I can say that, let us say, you can say that IA, IB, and IC are 3 currents. No load means 0. This is 0. But now there is a fault here. IA, so this will be equals to 3 of I0. This is called 0 sequence current, and this is nothing but IG, the ground current. I have already elaborated earlier also. Agree? So that you can say that, you can think about that. Or if it is non-zero, you can say that some part, you can say that of this one will be compensated at that. So this will be a little bit smaller in terms of that. So the ground current will be now, you can say that, will be same as the phase current in the phase A. Whichever phase is involved with the fault, that current will be flowing to the ground in this kind of situation, and so. So that is what we say that residual current, or you can say that, or the ground current, you can say that, can be obtained from the which one? From this current. This information is same. So therefore, what you say that in this process, if the 51 and so, or 50 and you can say is being used, they can also find the what is the corresponding ground amount of current by doing what? IA plus IB plus IC. IA plus IB plus IC. And that is nothing but called the ground current. They no need to measure, you can say that, the ground path current differently. Like in a transformer, I'll tell you like this. So we have a grounding here. So this current can be also measured. But this current is nothing but the summation of this current if you apply the KCL. Like that. So here in this case, this and this current is nothing but the corresponding IG. Okay. Now, how will you select the corresponding pickup current in a design process? This is going to more little bit theory in terms of that, but still then we'll go. Otherwise, the laboratory performance study will not be well understood, well taken. So pickup current setting, as I say that this should be normally higher than the load current level, and should be around or below. We should be below, you can say that, to the minimum fault current level. So that should be the guideline, you can say that, from this one. For a phase relay, as you know, is not involved with ground. What should be the corresponding selection process, and similarly will come to the ground perspective. So there is a ground, you can say that the pickup current should be Imax. Imax is the load current, maximum load current perspective. K is a factor. So the general guidelines, the overload factor we call, that for the generator it is 1.25 to 1.5 if we are protecting generator. For motor it is close to 1.05 times only to the maximum current. But for overall distribution lines and all these things, it is can be 2. So this is study reveals, and then with these kind of things, the practicing engineers set the corresponding relay in terms of that. So if you are using for a distribution line, you can use a factor of what is the maximum current expected to the system, and then accordingly twice of that will be a threshold for your pickup current setting in terms of that. But this is a general guideline. This does not hold good always. There are situations you can say that it may not be correct. But still, let us go by that. So pickup current should be below the minimum fault current, as I say. That is also another guideline for that. So this ensures that the protection, you can say that, C will be like this. So how will C select the pickup current? Pickup current should be greater than K Imax. For distribution line, it should be twice Imax, and it should be less than I fault minimum. So that's my point now. Let us say, you can say that we are talking about this is I minimum, I fault minimum, and let us say this is Imax level, and this is twice Imax. So what is the I pickup said? This guideline say that it should be greater than this and less than this. So I can select I pickup this. Okay. Let us see a judgment now. if my selection will be at this point. Let us say this is 5 ampere. Another one, someone will say that no, I'll take consider that 8 ampere. So what is the difference? Someone will say, I'll say higher I'll go. What is the difference? Or someone will say that no, I'll take consider that 4 ampere. So these are the different options. Now how that decision, how that consider pick up is, I pick up against that. Even if this guideline also, how that is taken care, that we like to see. So suppose you consider that we have a pick up this 5. If I go for 8 ampere, what does it mean? It means that many faults, which are having with some resistance and so, with some resistance in that path or arcing and so, cannot be identified. Okay? But you see here, if it happens to 8 ampere, even the load grows momentarily to a higher level, it will not trip. Good thing. So this is a good thing. But when the fault happens to be there with some resistance and so, and it could not discriminate, then this is not a good thing also. So this we call, let us say go for the 4 ampere. If you go for 4 ampere, all faults, including with a fault resistance also, will be identified. From the fault detection perspective, it is very good. But from the load perspective, any momentary you can say that happens to be there, load growth, it will trip, which is not good. So in these two, from 8 amperes versus 4 ampere with respect to 5 ampere, we see that in one case, from fault detection perspective, this is good, this is not good. From load perspective, this is not good, this is good. So we call two terminology in the design. This is called dependability, and we call security. And the commonly considered is the reliability of the protection system or the relay or so. Now, what is dependability? The relay depends. What is the purpose of relay? Fall, protect it. Go for tripping. That is about dependability. Security, no fault, remain silent. No fault where? In the assigned zone, in this line section only. It doesn't bother about other line sections or the transformer also, it doesn't bother about. That is about the security. So this asks for, you can say, a better selectivity. Selective way. Which section is faulted? That section should be only isolated. So therefore, in this 4 ampere versus 8 ampere, if I compare, 8 ampere security is better, dependability is not better, poor. 4 ampere dependability is good, but security is not good. So most of the systems, protection system perspective, what is required? Any fault, trip it. So we give higher emphasis to dependability. We give higher emphasis to dependability. That is what the design philosophy happens to be there. But if you go to the high emphasis, then there will be unnecessary tripping in the systems, even over a load perspective also. So when I visited a steel cement factory and so there are a lot of consider momentary and there are a lot of trippings in the system. So I asked you consider the corresponding settings and so they say that they are very high setting and all these things. Very high setting means you can say that many faults will be not detected. So in compromise, you can say that perspective, that if you require the performance of your system, operational performance, then in compromise, you can say that the life of the particular transformer's device or so. That is what the pickup setting. Selection of pickup for the ground now. So ground means this path, this, sorry. Okay, ground means you can say that this path, this current. So for ground relay, you can say that ground faults are more frequent compared to phase, as I told, involve this. Pickup setting of producer, a ground fault causes unbalancing. Now I say that one point here, during normal operation, as I said, IA plus IB plus IC will be 0. Balance system. True. The unbalance in a system is not desirable, and even in the distribution system, some unbalance and so happens to be there. So that unbalance will lead to, you can say, that current to the neutral wire, to the neutral L. IA plus IB plus IC. I can put IN also will be 0. Neutral current, all in proper direction, and so here is summation of all will be 0. Now, when it happens to be ground current, see here, phase A, B, C, and N. A, B, C, and N. So, and this is connected to the load of the system. So, even if we have unbalanced load, means single phase load. One load may be connected to the one single phase. A small house, 1 kilowatt load may be connected to only phase A. My house, we have load 3 kilowatt or 5 kilowatt load, so 3 phase supply there. So point here that when there are a lot of single phase supply, there will be unbalance. But unbalance means the corresponding neutral current will be there. But when you talk about the fault, it is not to consider neutral current. This current state goes to consider to the ground, you can say that goes to the neutral, the earthing part of the transformer, not this neutral. To follow the distribution. So therefore, when you say consider this part will be now non-zero now. Agree? So this is nothing but Ig. So Ig, you can say that normally it is 0 ideally, but some leakage current, or you can say that something will be there of the, let's say, cable, poor cable, and so leakage current from the cable perspective, and so leakage current only. That becomes very small. Agree? So therefore, this is a very sensitive thing. Whenever ground fault happens to be there, the current will be substantially high, but normally the ground current is pretty low, negligible, theoretically. So typically 10 to 20, that's why I consider the corresponding, that the pickup current you consider in this case is set to consider something like that, 30%, 20%. You can make it smaller also. If your system is very new and reliable, you can make a judgment and you can make it more sensitive. You can make it not 0.3, can we make it 0.2, 0.1 also, depending upon that. Whereas in earlier case, we did what in case of phase, we make it twice for a distribution system, twice of the full load current. Here you are talking about 30% of the full load current, 20% of the full current, and maybe even less you can do if the corresponding system is very good and other things. For high voltage, the setting it can be 10% also. So now the question is, which one is more sensitive? I told earlier also, which one is more sensitive? This ground one. And that's you can say that ground collars are more sensitive and they are more reliable to handle this things. So more sensitive. So now for pickup setting, consider phase relays. 3 phase faults are taken care, phase faults, and ground relay consider phase to ground faults are taken care in terms of that. Now you come to consider time information in the overcurrent characteristic and so. Agree? Overcurrent characteristic and so. Now you see here, overcurrent may generate trip command either instantly or with a delay. We reason it out to consider what is the reason of delay also. If the fault is not permanent, why not you can wait and watch some time. There are different considered characteristics of the relay. That is what the in terms of the time information we call instantaneous and we call time delayed. We have time delayed definite time. I'll show you the characteristics. We have inverse definite minimum time characteristics. Inverse definite minimum time. There is minimum time and inverse also. Moderately inverse, very inverse, extremely inverse, depending upon the characteristics. I'll show you the plots in terms of that, and then we'll go one by one and we'll see. So this time, when it is instantaneous, we call number is 50, no delay, and the characteristic becomes like this. We call time y-axis and the current multiple of pickup current. So what you call consider clock setting multiplier, PSM. Remember PSM, clock setting multiplier, or multiple of pickup. Pickup, you know, I pickup, multiple, how many times of pickup? I relay, current to the relay, divided by this I pickup. So this pickup is nothing but setting. So relay current, whatever current is going to the relay means system side current, fault current, divided by the pickup. So suppose I have pickup of 8 ampere, then I will divide by 8. Suppose I pick up current of 4 ampere, I will divide by 4. So how many times you can say that the corresponding pickup current is the relay current at this moment, at this fall, for this fall, that will be there. This is called multiple of pickup current or PSM, not the relay current. It is divided by the normalized kind of thing to have a comparison between different characteristics. So, and then this is time. So in this case, no delay, instantaneous, and it goes trip. Anywhere you can say that is tripping, and beyond this you can say that no trip. Time is very high, infinity theoretically. But this current, no trip region. But within this region, no delay. So this is what the characteristic you can say that for this one. Well, I think if you so you can say that is about 50. Definite time over current relay. Also we call 50 definite time. Similar to that. Here what is that? It keeps some time. So you can say that operating time or the definite time over current relay is fixed. It is a fixed time. We delay, put delay. In some applications it is useful. And what we have a flexibility about changing the corresponding delay, high, low, and all these things, because of different applications requirement and all these things. Agree? So that's you can say about that. Now the time current characteristics. Those are either no delay or with a delay. Now we talk about inverse definite minimum time or 51. Now what is that? You see here there are three curves. This is IEEE curve. There are different, you can say that standard agency, and accordingly different curves are there. So let us you can say that, see what are the, you can say that we call moderately inverse, very inverse, and extremely inverse. So you see here extremely inverse lower curve, moderately inverse middle curve, and then the very inverse is middle curve, and moderately inverse the upper curve. For a given pickup setting means pickup means what? Pickup means for relay current divided by the psi pickup. So this current is proportional to relay current or fall current. Relay current is fall current. So for a given fall current, the time of judgment, time of trip decision by extreme inverse is small, very inverse is little bit higher, and moderate inverse is much higher. This is what the characteristic of suggestors. So this is about the operating time in second. So the operating time versus the pickup setting, the multiple set PSN, clock setting multiplier, or multiples of pickup, multiple pickup compared to the pickup things, how many times of the pickup gives us this kind of thing. So what we see here, that at different, you can say that for currents, the corresponding time, you can say that is different. So even if we for a relay, there is no need to fix for all three. For a relay, at a particular locations, we will fix only, you can say, out of these three something. So this for you can say that will come, you can say that more on others of options also. So you see here, suppose this is a system, and how the relay takes it decision and how the time varies, that we like to see. So this is IDMT, and we have another options called time multiplier setting. Another setting, pickup setting, types of characteristics, inverse, very inverse, extreme inverse. There are three in the IDMT. In the IDMT, we are talking this distinction about IDMT type, inverse definite minimum time. What is minimum time? I told you earlier, what is minimum time? This is the minimum time. This is the minimum time. What is inverse? This part is inverse. Where the inverse is coming? I square RT. Okay? This I square RT is given the inverse. Large current, small time, small current, this. So if you see, you can say large current, this is the large current side, small time, and then minimum time. IDMT, widely used, you can say that in the industry in terms of that. So time multiplier setting, TMS, or time dial setting, is time control. What is the time control? Like in that fixed things, what you do here, if you see this, suppose this is any curve of, you can say that moderately inverse or so, IEEE curve or so. So this is 1, this is 1, I'm marking it 1. If I multiply with that time, it will be 0.5, so it will be lower. If I multiply with 3, it will be larger or so. So TMS is a factor. If I multiply that factor, then the corresponding decision time is like I can say here any instant, any time here. same current level divided by the pickup setting, same PSA, the pickup, the multiples of pickup or PSN. So you see here, for 1, this is the time, for 0.5, this is half, and for 3, you can say 3 times. That control is also there with the characteristics, IDMT characteristic, and that is what we call, you can say that the time multiplier setting. So what you do, I'll show in the formula also that how this can be used, considered in terms of for the relay characteristics variation. So these are the different options available in the numerical relay platform. You can change the corresponding characteristics curve. Each one is a characteristic curve. You have to pick up which one will be useful for a particular locations and particular application and so. Now, what we say in this perspective, let us say here, in this case system, let's say F2 position and there is F1 position. So if we are looking at this relay, F1 is further and F2 is closer. So for a F1 fault, the time of decision, because current will be smaller, from this side current flows, current will be smaller, so decision time should be more. Again, I square RT governing. And for F2, this is for F1, and for F2 you can say that again, fault level is higher level of fault, so current time should be smaller. T2 should be smaller than T1. T1 for F1, T2 for F2. Agree? Now let us see what will happen here. So here you can say that if you see here x-axis, so any curve we see, let us say I'm talking about T1 curve. This is the T1 curve. So F2 fault current is higher, so that's why this PSM will be higher. So this time of this T2 is small, and the F1, the corresponding current is small, the T1 is higher. So you see here T2 is less than T1. So if you take any curve and then use it, and you see that you can say that the corresponding time information is being obtained purposefully. We'll see application perspective. These curves can be being expressed in terms of the IEEE has defined those, you can say that mathematical expressions, and the mathematical expressions for this is this. Now, what is the decision time T? The decision time T is in terms of K upon I. This I is the current, which I, this I is the current, relay current. So the relay whatever current, that is the system fault current level, divided by this I pickup, the setting, power alpha, whole minus 1, plus L, a constant, plus the TMS, time multiplier setting. Time multiplier setting, earlier we were discussing. Okay? So this characteristic, any characteristic curve which we saw from this time versus this corresponding PSM is governed by this equation. Agree? So that is what we say in terms of that. So for this, you can say that if you see the corresponding IEEE curve, moderately inverse, very inverse, and extremely inverse, the expression you can say that in terms of that, alpha 0.02, K 0.05, and L 0.114 for moderate inverse. So we put this corresponding value, which are already standardized and given by the manufacturer, including in terms of the IEEE material also. So we put this, you can say that, then whatever curve we get, accordingly you can say that that curve is called the moderately inverse, very inverse, and extreme inverse. And you multiply the TMS like 1, 0.1, 0.2 to 1.5, depending upon the availability in the particular relay. You can again control the corresponding time. You can make it faster if you multiply with 0.1. If you make it delayed, if you multiply with 3. This is, you can say, the options you can have. And why do you require that? We'll see later in terms of that. Okay. So this by controlling this alpha, K, and L, you can control the characteristics of and all these things in terms of that. You can have numerous things. I'll say you can say here. If you see here, same equation you can say we are using in terms of that. So for this same you can say that IDMT characteristics, very inverse, extremely inverse, long time inverse, Arriva has that. So what I like to say that these are against the different standards, manufacturers, and they have their own standards, and so we use here in this case our discussion anciently. If you go to the relay, all things are available. You can pick up this or that. But what is being done, that the corresponding distribution agency, they go by 1. Otherwise, it will be too complex and too, I'm sure that future generation they cannot make any. It will be troublesome for diagnostics perspective and so. So in our analysis, we will confine to only the IEEE perspective, but we have other, you can say that things also not limited to this one. There are each, you can say that manufacturer have their own, you can say that calls and so also. Fine. So what is the flexibility with the numerical 51? 51 means IDMT characteristics. You see here, three things are there. One is pick up setting, we can change. You can have a TMS change, as I say, and you can have chord shapes, very inverse and very inverse. So this is the call, let us say, what things you can change. If it's TMS, if you can make it 0.1, then it will go down. If you give me 0.3, it will go up. That is one option. I pick up, if you can shift this, consider to this side, I pick up here reducing. And if you can say that go to the right hand side, then I pick up here increasing. See, beyond pickup, less than pickup current, the relay does not trip. It means that time is infinity kind of thing. It will not operate. And greater than you can say that pickup, the things will trip. And how it will trip? Because very large current, time decision is small. And then we have a definite time after that. And if it is a medium level of current, time is also accordingly. Now, the shape of core is nothing but these three: inverse, inverse this, that K, alpha, and L will govern the corresponding shape of core. Three dimensions that the flexibility in the having the shape of the characteristic, rather we call, of this IDMT in terms of that what we are using. So TMS flexibility, chord shape flexibility, and pickup flexibility. These are the three things. So we started with overcurrent relay, simple thing, current high, it should trip. But now we are going to more and more complexity in terms of that. So someone will say that why you are going to that complexity and things. We'll see applications how that can be useful in terms of the time information, how that is being useful in terms of that. Coordination or phase overcurrent relay. Similarly, you can go for ground also. But phase and ground can say relays are coordinated equally. What is coordination? Try to understand that. So let us say this is the system source. We have a bus where load is connected. We have another bus, load is connected. We have another bus, load is connected. High voltage, low voltage, whatever system may be there. So we can say that in this arrangement, we essentially require, you can say that two relays. Let us say at bus B, we have RB relay, and bus C, we have RC relay. Think about a fault at F1. All of you. I think if you require clarification, I'll explain you what is that coordination you should understand. For this F1 fault, current will flow from this to this path. So this relay will see also same current, this relay will also see same current. Both will see same current. But which one will should trip? If RC trips the breaker here, this load and right of all, you can say the loads will be affected. No. From selectivity point of view, which we were discussing earlier, RB should trip for this F1 fault. Then only this portion will be out of the service till the fault is being removed. So this load can be still made, can be still fed, considered from the source side. So that is about the selectivity. So therefore, for F1, RB should trip. Now let us say situation happens to be something different.
Sir, can you just explain this part again?
See here, system you understand that this is a 3-bus system. Load is connected here, load is also connected here, load is connected. Otherwise, you don't require bus also, unless there is some utility. So this is source substation side. So fault happens to be at F1. I am discussing about this fault only. So for this fault, current will flow from this to this. So this relay will also see current, this relay will see current, same current, IF1. I am putting it IF1. Now what will happen? That the question is that if they will see same current, who should trip? It will may confuse. Who should trip? We say that RB should trip because if RC trips, this load will not get the supply. But if RB trips, this load will get supply. So from selectivity perspective, we prefer that RB should operate at that time. Otherwise, unnecessarily consider that some of the loads will be out of operational. So that means that the RB should consider there, but how will achieve that? That is one question. Another question comes here. Suppose there is a possibility that this breaker here is a mechanical switch. With time, that may I consider that is unable to open. Is unable to open. Then what will happen? This fault will continue because this is duty of RB. Fault will continue and continue. So it will go on damaging. It's a problem case. So this is not good to avoid. Furthermore, RB is a relay. From relay to breaker, there is a command and there is a communication. The communication wire is being damaged by rat. The battery is not functional. The coil, trip coil has some problem, and so. So any device, any arrangement has certain problems. Hello? Yeah. So then what will happen? So if you have a problem in opening the breaker during that time, due to whatever reason, or the relay has a problem, the relay itself will have a problem. Or the relay characteristic is said that it is not able to find that fault. Your setting is improper. I put it into maintenance, and after the maintenance, I restore it, you can say that, I fit it, you can say in the cabinet, but somehow it is not an operational. Then in problem. In that case, this one acts as a backup. The RC acts as a backup. You understand what is RC backup? So what will happen that the RC here waits for some time, delay, delayed decision. If it waits for some time and watches and then say that no, there is a problem with something, and then it opens here. Is it not good? It's good. It is good for the system. So this is called backup protection arrangement. But then RC never should operate before the operation of RB. So therefore, the backup, the delayed decision delayed with respect to operation of RB, how much delay? That will require a coordination. Coordination between RB and RC relay. Like in an IDMT characteristics, I can say here, if this is the corresponding relay for RB characteristics, RC relay should be here. Is it okay? For the same, you can say level of current. This is a time information. This is multiples of PSM. Same level of current, as you notice here, the decision time RC should be more. Wait and watch. How much time? Typically, what is being done, that when RB takes its own decision time plus the breaker opening. The breaker opening time, we can say that typically 2 cycles, 3 cycles, and so. So 40, 50, 40, 60 milliseconds and so, typically, not necessarily minimum kind of thing, plus the relay time decision. Commonly all this arrangement and all uncertainties and all taken care. So typically 10 to 15 cycles are given. And this is nothing but 0.2 to 0.3 seconds. So after a delay of 0.2 to 0.3 seconds, because of the breaker and all operations here, this relay should operate. This relay should command the breaker to be open. Is it clear? So this gap, you can say that is the coordination time we call between relay RB and RC.
Sir?
Tell.
Sir, also sir, in a system, like how do we determine at which positions we need to install the breakers and the relays? Like how do we determine the positions?
Okay, good question. So this is about the protection philosophy. See, protection and relay also big investment. So if you do, you can say that. So what you say that? Suppose you can say that we have a transformer here. See, these are feeders. So from here you can go to another line. From here also you can go to another line. So we have a transformer here and feeding this also. Agree? So now you can say that we have a breaker here, it may be breaker here also, like with a transformer breaker here also. So you'll breaker here also, breaker here also, breaker here also. Now what will say that, as I was telling, you can have a breaker here also. If you put one breaker here and don't put any breaker here because of the cost associated, then if you treat this, you can say that whole, you can say that all customers, thousands of customers will be affected. Would you follow? So therefore, what is your, you can say that, provision? No, you provide that this will be having hundreds of customers. I can put like this. For these 100 customers, I can put a transformer of, you can say, let's say 100, you can say that kVA or 1 MVA, and I can put a breaker and relay element and so. Agree? In CSE Kolkata, they don't have for LT system breaker. They have only HRC fuse and so. So my point is that what your question is that what to put breaker and all these things. If it is a radial system like this, you don't require breaker here, you require a breaker here. You don't require breaker anywhere. And the fault can anywhere fault happens to be there up to this direction. This is bus A, this is bus B, and this is a line. So you put a breaker here, then you can say that a relay here, then that is sufficient. When you go to the upstream side, again you can say that if you load here or bunch of loads here, then you require a breaker here. And how do you decide that whether investment is worthy or not? That you decide. But your question is another valid question. Right? Like you see here, system here. When you go to the high voltage system, I have interconnection like this. Current is fed from this. Our 400 kV network in the power system is a loop system. Our 765 is a loop system. All are interconnected. Sources are from both ends and so. So a fault happens to be here. Current flows from this side and current also flows from this side also. Agree? Now in this case, if you require one and only breaker, but still you can say this fault will continue from this side. So you require breaker at both the ends, here also, here also. Breaker means relay also. Agree? Breaker cannot operate okay normally. Is it okay now?
Yes, sir.
Now phase overcurrent relay coordination, both by time and current. So coordination by both time information and current information. Agree? Phase overcurrent relay coordination both time and current. So in the identity characteristics, we got that because of that reason. We understand now why require the coordination to have a backup now. So see this utility of this curve now. So in that case, you can say that for this arrangement for a system like this, RB and RC, how we can coordinate that we like to see. So for the phase you can say that, and then similarly you can go to the ground percentage. So how the coordination will be achieved, that we like to see. What are the guidelines for that, and how we'll do that. So two things we have to see: time and the pickup setting. Time means time multiplier setting, TMS, and you can say that current means pickup setting point. These are setting related of the characteristics. And this is about the characteristics. Either we pick up, we can say that IDMT very inverse, extremely inverse, or moderately inverse, and so out of these three. So first is the selection of the CT. 100:5 or 100:1. These are the standard thing. 1000:1, 400:1, 200, 300:1, and so. How do you decide that? What is being decided that you have this, you can say that rated current or maximum current of the system, which you know. So that is guideline for whether I take 100 or whether I take 200 or whether I take 1000. Once again, based on your load current, you decide, you can say that this side. And the secondary side, you can say standard in your distribution system or in your, you can say that power system, whether you use 1 ampere CT or 5 ampere CT. That 1 ampere of 5 ampere CT secondary current during normal situation. And this side, you can say that the ratio of this side is taken care from the load current. Even in the distribution system, in 5 years down the time, if you are planning for that also, the load may grow. So that maximum possible load you expect, accordingly considered, we set this one. But cities are not available 101.101:1 or 105:1. There are standard cities available 100, 150, 50:1, and so like that. So you have to pick up that. Set the pickup current for which the relay must operate. We know it using load current and the minimum fault current. The relay settings are first determined to give the shortest operating times at the maximum fault current levels, and check to see the operation is also satisfactory with the minimum fault current. I'll tell you on this. This is important. TMS for the primary relays on a figure is selected are the fastest possible things, usually correspond to the minimum TMS. That will know. Relays are coordinated for maximum fault current. Relays are coordinated for maximum fault current. This is important. Seen by the relay, not for the minimum fault current. TMS for backup relays is selected based on the coordination time of 0.2 to 0.4 seconds. That 10 cycles to 20 cycles I was telling you. Now, one point here, two important points. Suppose we have a set of curves given that we have pick up and say that this is the IDMT curves available for the relay. Relay has all IDMT curves. Let us say we are talking about IEEE inverse curve or so. In that case, as I said, the lowest curve, remember, the lowest curve is assigned to the extreme end against the relay. Here in the extreme end relay, RB, the lowest curve is assigned to that. And then we go on adding to the left towards the suppression side, one after the other curve. Understand? To have the provision of, we can say that, of your backup. Otherwise, you cannot do. See? So therefore, that is the mechanism. The lowest curve is assigned to the extreme end, you can say that, breaker or the relay, not breaker, relay. Agree? And then you go on adding up and up, you can say this. But what happens? There is a problem with that. If you take arbitrarily, you can say that, and even if you satisfy the coordination, you see, or from the same, you can say that fault current level. If you take an upper curve, the decision time becomes more. Then you have to take further upper curve. Therefore, the decision time becomes when the but the decision will be more and more. Is that there is a break, Kuldeep? The presentation is on.
Yes. No. Yeah, the presentation is on.
Is there?
Yes. All are there. Yeah, I can
Are you
hear.
able to see the presentation?
Yes.
Okay, fine. So somehow time missing that. Okay.
Okay. Some network disturbance occurring.
Yeah. So here in my presentation, I'm able to see you all, not to. Okay, fine. So whenever you find problem, you tell me. Now, what happens in this case? You see here that this is the problem. So therefore, we have to take the bottom, the lowest curve. We can say that for these extreme end things, and then we can say that the other, you can say, things will go on adding upon that. The other, you can say that important point, fifth point, which is say that the relay coordination should be maximum fault current seen by the relay. Now see here what happens here. What is maximum fault current? What is minimum fault current? When the maximum fault current happens to there, we are going to the right, and when you go to the minimum fault current, you are going to the left. This is about the divided by this pickup current. This is PSN line. If you see this portion of these, the time difference between these two, any two curve, is smaller as compared to the time difference here. The IDMT curve. So, because we have to maintain that coordination time of 0.2 seconds or 0.3 seconds or so, coordination time. So coordination time will be ensured if you do consider the right hand portion, that is maximum current level, not at the minimum fault current level. If you could maintain the minimum fault current level coordination time of 0.2, right hand side it will be less. You follow it. So therefore, when you are going for the coordination of 10 cycles or 15 cycles between this relay and this relay, you maintain it what is the maximum fault current associated in that arrangement. So you do in the right hand side, not in the left hand side. Then you ensure that at a minimum fault current level also that coordination time will be maintained, it will be more. Is it okay? That's the consider from the curve you understand. From this curve right hand side, the gap between any two curve you see here is small as compared to the gap in the left hand side. Time gap. So that's the yeah, tell.
So like as you said here, like can you like show that sorry, yes. Sorry,
Yes.
here sir, as you said, like RC should be coordinated with RB. Like if RB fails to break the circuit, it should wait, and after some time, it should like break itself. Like this is when the fault is at F1, right? When the fault is at F1. Now if the fault is at F2, in that case, RC should break like without any delay. So how is that achieved? Like
Yeah.
you've not.
So now let us for F2 the current will be high. Agree? So let us say I'm taking two curves, as you are saying. I'm taking two curves. This for RB and this for RC. Is it okay? Assume. Now, what do you say that for F1, you can say that this fault current is here. For F1, the remote fault, the fault current is here. This is F1. For F2, the fault current will be more. Agree? For F2, who will see the fault current? RC will see, not RB. RB will not see. Yes? Only RC will see. No fault current. Fault current will be this. Agree? So this F2 fault, IF2, and this is corresponding trip time. Is it clear? Could you respond? Is it clear or not? For F2, this is the path, and for F1, this is the path. For F2, only RC will see. For F1,
Sir, yes, sir. Like when we'll be determining the like coordination time for RC, like it will also won't it also affect the trip time for F2? Like
yes,
the entire
it is
curve will
affecting.
get.
For RC, it is affecting. So that's a delay. I told you that. That is a demerit of the system.
Yes, yes, yes. Understood.
Very
Sir.
correct.
Okay.
Yeah, so it is delayed of the system. But if you don't do, then backup cannot be provided. Is it okay? If we don't do, then backup cannot be provided. So that's the demerit of this. What you say is very correct. Yes. So you can say same operating current, not to lead to confusion and so. The relay farthest from the source should have the current settings equal to or less than the relay behind this. This is a guideline for that perspective. We'll see an example and then I think we are converging to something and then we'll go to the laboratory testing and so. Phase over current relay coordination, IDMT characteristic in a radial system. Radial means unidirectional power flow. Agree? There is no source to the right, so it is not. But in the today's power system, distribution system, we are putting a rooftop and so, there is all possibility that current can flow from the right also. Okay, we are not going to that right now. So these are the different loads connected in terms of MVA and so. And we have some impedances of this path also, like this. And we have a fault created here. We can fault create here also. Now our job is here to how to have this actual coordination between RP and RC for a given characteristic given and so. For fault at F, RB is the primary and RC is the backup. RB is the primary and RC is the backup. Agree? So that we have to see in terms of that perspective and so. Okay. So if you see this, so what is being data required to have this corresponding coordination tasks is that set of data for RB and RC. Maximum load current 58 is observed by RB, 115 is observed by this. So there is some load here, so both loads are added in this. Minimum fault current observed by minimum fault current for RB is nothing but F, the remote point, farthest point. So 578 face-to-face fault. And the for the corresponding RC, the minimum fault current considered, which is having at this is about 136. Actually, this minimum fault current for RC should be also, RC should take care from what to what? From here to here. So this will be also 538 ampere. Agree? Maximum fault current for A, this is our boss level. Agree? Boss relay. So this boss you can say that gives you, sorry, this is not correct. This is 1036. If we create a fault here, it will create, you can say 578. We'll see that analysis. Now maximum fault current at A is 965. If you create a three-phase fault, not A, sorry, this B, 965 here. And we create three-phase fault here, you can say that this gives you 2580. So this is about, you can say that from simulations, you can say that network modeling perspective, the data are available, which is being used by the protection engineer for setting up these things. Clear? So this is what is being used by different engineers. So don't confuse. At different bus, we have created fault, and then we got the corresponding relation. Now, what is to be used and all these things, we'll see in the next slide. So now our task, you can say that to coordinate between RB and RC, RB and RC, how to do that. So we got, you can say that CT ratio of 100:5 and 150:5 is being selected. I told you that how to select the CT based on the current level. In one case, we got something like less than current level, say like 58 amperes. So I pick up the 100, and here it is 150:5. Here 100:5. So that is what CT selection. Then pickup current setting based on the corresponding full load current. We say, you can say that, and the minimum fault current, and the full load current, high full load current, maximum current. We select 10 ampere here, 10 ampere here. Agree? And the corresponding, you can say that what we do is that we, for this perspective, we corresponding TMS, you can say that, is being 0.1 and 0.2. How will do 0.1 and 0.2? You see here, I'm explaining here. So coordination time. So you do, you can say that the corresponding from this table, let me say from this table, maximum fault current. See, one point clarify here. RC acts as a backup for RB. So jurisdiction of RC is from here to here. Jurisdiction of, you can say that RB is from here to here, up to this point. So minimum fault current to which you can say that RC should take care is again this 578. 578 for both RB and RC. And the coordination between what? Now the fault, you can say that which you create at here, three-phase fault here, that is maximum fault current seen by RB, and that is nothing but 965. At 965 ampere, you coordinate between this and this, and at that time you keep the corresponding curve of, you can say that RC to be higher than this one. So this is what you can done for this perspective. So you see here, you can say that the multiple of, you can say that pickup current comes out to be 4.825, and you can say that for that you can say that the corresponding time is 0.14 for what? For RB, and you add, you can say that 0.3 second here. There is the coordination time. So that is, you can say we got 0.44. So we got from this side to this side, and then you can say that you can say that this side to this side and this side to this side. This is about the corresponding ESM for the maximum fault current at B as seen by relay RC. So you got this one, and you get the corresponding intersection of these two. If there is no curve at that point, we take the next curve. Okay? So this is, you can say that if you see the lowest curve is assigned to, as I already mentioned, is to the extreme end, you can say that relay RB, and the next curve you can say that goes for RC. So you got, you can say that here, let's see here 0.1 and 0.2. So as per the reliability, this is 0.1 TMS, a 0.1 TMS for RB, and 0.2 TMS for RC. This is what we go in terms of this coordination perspective and all these things. If you find problem, all these things, see this our video lecture. It will be more clear also. Or I think Kuldeep is recording this one. They can go by that also. So the objective in this experiment, overcurrent relay experiment, is to verify the operating characteristics of the numerical relay. Which characteristics? The characteristics we talk about, IDMT characteristics. Which one which I have said, is that the corresponding relay is following or not? That we like to see. Really? So that is what we like to see. So same arrangement as I already mentioned, we like to be in the circuit diagram, physical circuit diagram like this. This is our relay, MICOM P154 overcurrent relay. And what we do, we have to inject current to this one. So for that, what you do, we have an auto transformer here, some resistance controlling the current, and we have a CT here, 10:5. And we inject current to this one. This is our experimental system. Earlier we are talking about theoretical things. This is a contract, this is a breaker here. This breaker can be controlled by this strip coil, which is having a DC supply to energize this coil. And then you can say that from this end, with this the trip command comes here, and this to open or break the corresponding things. This is the input current, you can say that terminals for this case, and this is the output terminal in terms of this. And this relay requires power and this power supply is from the 110 volt AC or DC, both you can inject. This is what the structure, the overall arrangement also. What you do is that you vary the corresponding auto transformer voltage, then the current injection through this path becomes this. This is a short circuit low impedance path. So depending upon the corresponding voltage we are applying here and the corresponding resistance setting, you can get different currents here. So what you do that to this relay, you inject different currents. We have a pickup setting in the relay. We have selected, you can see that TMS, we have selected, you can see that a characteristic also, we'll see. And then you inject current greater than the pickup setting, and then you note the corresponding trip time. How will note the trip time? Because I told you consider the once it the command opens and the strips. So there accordingly you consider the corresponding relay, you consider records the things which you can see, you can get it from the PC. So for this case, these are the characteristics earlier I was telling about that we take consider TMS in this relay, consider TMS variation scope of 0.025 to 1.5, 0.025, very small. Agree? And then for our case, you consider in this case, we took consider 1 ampere pickup setting. In this example, we'll have more examples you consider for different settings also. And then you consider that we have time multiplier setting of 1 in this one, in this example, and the corresponding curve we consider IEEE curve we have taken. And there is a moderately inverse. Okay? Moderately inverse. CT ratio is 10:5, as already mentioned. So these are considered the corresponding things which are available in the relay and all these things. We can have a look on glimpse of what the relay provides. And then we took the observations you consider for different fault current injection. This one greater than the pickup current, greater than the high pickup current is 1 ampere taken for this system side. And then what we do that we noted out against that this in the tabular form. So what we see that this is about relay consider timing given. We see that in terms of that. So trip time and the we created you consider phase A to ground. Other phase you consider currents we make it 0. So this is a phase A to ground fault and this is a ground relay. Not phase relay operation, ground relay operation. This is as such a ground relay. So this is the current input, and this is the corresponding time you can say that which is we are getting for the decision time. So if you see here, you can say that for 1.36, this is 9.26. For 3 ampere, it is 2.43, much lower. So if we go down, you can say that the current you can say that being increasing 9.28. The corresponding time is 1.265. 1.265 is 1.28, 1.3. So you see here it is very close to 1.3, and this is the minimum time. Inverse, definite, minimum time. So this is the minimum time we are talking about. Okay? And as I say, you can say that these are the constant terms. TMS is 1, IS is the setting is 1 ampere, CT ratio is 10:5. We are scaling down by a factor of 2 only. Fine. So this is how we can say. So for example, here if you see at this time, this you can say that the time is 1.645 for an injection of current of 5.34. But you are using this equation, this curve we are using. So if you substitute the data L, K, alpha and so, then you are getting for 5.3 ampere input, the corresponding time calculated is 1.625. Calculated current, simulated, calculated. But the actual one from the laboratory which we are getting by that injection of current is noted only 1.645. So this is the some discrimination we are getting. Those are the factors of, you can say that circuit breaker opening time and then so and so, uncertainties in terms of the measurements and so on. Whatever current we are measuring also, how good is our CT ratio and so and so. We are talking about 10:5, it may be something different and so on. So what do you say that for this set, for this case, these are PSN current versus divided by this pickup setting. Pickup current is 1 ampere. We got this, you can say that these factors, and then we noted down these points are there, which are there in this table. And the line, solid line, you can say reference call that you are getting from, you can say that from the your equation data. The equation data there that you should follow that. So this solid line is your nothing but a reference. And the dots you can say that, or stars you can say which you mark, are nothing but the experimentally verified. So what you see that this is an identity characteristics to the reference curve, which is the based on the equation, the corresponding simulated one after injecting and the tripping, actual tripping by the relay. The stars mark you can say here points. They are following the curve. It means that the relay is good one. So that is the verification we are talking about here. We say that the relay is following as per the manual provided by the manufacturer. Agree? This is verified in terms of that also. So we have two TMS now, 1 and 0.5. 1 and 0.5. And you found, you can say that, which is 0.5? TMS is multiplied to the equation, so lower one is 0.5. And you can say that we verified with that two sections also, and we say that you can say that they are in almost in agreement with the reference, and the reference is nothing but from the equation. So this is available in this YouTube intro. So what are the tasks for this lab? Report submission. Everything should be handwritten. We need plots of the overcurrent relay. We'll provide you 4 sets of data. Kuldeep will upload in the Kuldeep, it will be in time in the Teams.
Yes, sir. Yeah.
Okay.
In file section, yeah.
We will do the needful. So these are the data sets we'll provide, 4 sets of data. And we have to plot them in the graph. How? Similar to this. Like plotting of this. So here we have a reference curve. 2 curves we have to plot. Reference curve from the equation, whatever is given. And we have, you can say that your points, you can say that which will plot. And then see that whether it is following or not. If it is not following, if you have to justify, like in the lab we do, and something like that. Agree? In most of the cases, you'll find that they are following the corresponding things because the relay is very reliable in that sense. So the other one you can say that reference curve you can say that calculate from that you have to go. And then let's compare the reference curve versus the data obtained. Good, bad limits we have to do. Can there be further improvement like here something like some difference you'll notice? What may be the cause, and you can say that root cause analysis you can tell in terms of that. The fifth one point, relays RB and RC are 100:5. Maximum fault current at base, all data are given like what we have seen earlier example, and the corresponding curve is also given. So then you have to consider go for the corresponding this. If the coordination time interval of point C is comment on the TMS setting of the relay system. You should only have about the TMS setting which is there. You can set here. Is it proper? Not proper? Is it satisfying the requirement of coordination or not? That you have to tell. Okay? Here in the 0.05 for this system, given the data. 6, you can say that in the 6 we have a system like this, and its MATLAB model will be provided to you. Is available, provided by the they will upload that, and the data sets are there. Table 1 is there. You have to fill up this data only. A table, you can say table 2. Table 2 you can say that. Write your roll number. Write your roll number. Last digit of your roll number will be RF. What is the RF? Whenever you are creating a fault, we have a scope. You can say that in that path you can put an RF, arcing resistance, and so. So depending on the RF, the corresponding fault current amount changes. So accordingly, you consider the corresponding trip decision time will be different. So you know your roll number, last digit 0, 1, 2, 9. So you put that value of RF for creating your fault. And then you consider for F1 and F2, this is F1, F2, and F3. F1, F2, and F3. 3 locations. And we have RB and RC relay, RB and RC relay. And we have current. What is the corresponding current? In that meter current will be showing. What is the corresponding time? Time of simulations you can get, you can say like this. The corresponding in the simulation means in your relay. Which relay? MATLAB model relay. Model based relay. And time of reference. Reference will come from your equation. From your equation. So So this you can say you will be your comparison. So you compare this to this to this, this to this, and make a remarks out of this. Once again, this part is nothing but all data are given and the corresponding equations which is being used for the relay is this. So we have a MATLAB model to explain that how the relay functions. In that MATLAB model, you generate the corresponding current data and that will also treat time also, both I and T. So both I and T you can note down for creating fault at different positions with your own RF value that depends on your roll number. And then you can see that you can put it down here and you find the calculate the corresponding current time, you know the current value. Find the time value you can say from this equation and note here also. That is your reference time. This is all we require from this. And these are the pages instructions where what to be written and all these things. You create a PDF file, single PDF file, and Kuldeep will instruct how to upload them also. Okay. So this ends from my side. If you have any questions, queries, welcome. Please, question, please.
Hello, am I audible, sir?
Yes, please, go ahead.
Sir, will you share this slide on Teams?
Every slides, video can be provided also, Kuldeep?
Yes, sir, it can be uploaded, but better they can go through the link.
Okay, fine.
Okay, link we can provide.
And we are also at YouTube, also that for this session perspective. But slides and all the details will be this will be slides will be available.
Excuse me, sir.
Yes.
So we have to submit this before, like, what's the deadline?
So Kuldeep, next week, because you'll have another exam next week.
Yes, sir. Yes, sir.
Okay, next week.
So, and where we will have to submit this?
In the Teams, you can say that Kuldeep will circulate a mail to all. Is it possible?
Sir, we can create assignment here only. I think they may be familiar with assignments here in Teams also.
Yes,
in Teams platform. Yeah. Okay.
Okay. In Teams platform, assignment submission will be also there. You write your roll number and for us. Is it okay? Anything else? If you have any query, Kuldeep, can you in your message box, can you give your email ID?
Okay, sir.
So then, anybody has any questions again, theoretical pursuit also, you can ask Kuldeep. I am also there, ready to help you. Consider any query, any questions you consider regarding this also. Not only submissions, anything related to the.
Sir, I want to tell one thing.
Yes.
In the Simulink model, like those who have 0 as the last digit of their roll number, they are supposed to put 0.01 as fault resistance because the model throws error. Yes,
okay,
yes.
so there will
Because
be
the model 0 it throws an error. Okay.
So those who are having 0 roll number at the end, you put some value 0.01 also. Agree with this one. I think in the Kuldeep in our slide we write down. Agree?
Okay.
Okay, done. Anything else? Any question?
Sir.
Tell.
So like I had a doubt regarding the theory part. Like sir, can you like explain that part again? Like how is the ratio of the current transformer chosen? That part I'd like to understand.
Okay, so I show you that the ratio 100:5 or 100:1.
Excuse me, sir. Sorry to interrupt.
Yeah.
So, like, from your side, like the theory part is over, right? Like, can like the people who want to leave for dinner, can they leave?
Yeah, please leave. Yeah, most welcome. Please leave. Yes.
Thank you, sir.
Yes, my presentation is over. Anything? Okay, please leave. Okay. So your question is 100:1 or 100:5, 1 ampere city or 5 ampere city. So I told you that maximum fault current, what is expected in that system, let us say line, distribution line, that is the consideration for the city ratio. But again, city ratios are not arbitrary. They are standard city like 50:1, 100:1, 150:1, 200:1, like this. Is it clear?
Okay, sir.
In that case, we got 58 ampere. 58 ampere will not be available. So next higher level you can think of. Okay. Thank you all. And we are leaving. Kuldeep?
Okay, sir.